Hello and welcome back to the second part for lesson 6.2 video. We're talking about the normal curve and we want to find the z-score that corresponds to this given area. So we're looking for this z here down here. We know it's area to the right. So it's z of 0.0461. And this is the probability that z is greater than some z area equal to 0.0461. And we have to remember when we put it into Desmos, we have to put it in as 1 minus this area because it only accepts the area to the left. So it's going to be the inverse PDF of the normal dist of 0, 1, comma, 1 minus 0.0461. Now, because the z-score is symmetric, we can put in 0.0461. It's just going to give us the negative z over here that matches. So I'm going to show you that in Desmos. So up here, I put in just 0.04061. It gave me the negative 1.68. And if I put in 1 minus that, it'll give me the positive 1.68. So that is the z-score that goes with this area, 1.68. And we can validate that. If we run it to 1.684, we can put it into our normal distribution and turn on the graph and see that it matches what we want over here where my mouse is. So you can check that by putting it into the normal dist into the graph. So let's move on to the next example here. Letter D says, find the z-scores that cut off the symmetric middle 90% area. So when we want the middle 90%, that means we have two z-scores, a negative z over here and a positive z over here, and we want 0.90 inside here. That means we have two equal areas outside here. So we're going to take 1 minus 0.90 and we get 0.10. And then we're going to divide that by 2 because these are equal spaces. So there must be 0.05 here and 0.05 here, and these should add to 1. So I'm going to look for the negative z of 0.05 and the positive z of 0.05 in Desmos. I'll show you how that works here. So I'm going to put in, so it looks like 0.05 to the left is a negative 1.645. That's the positive one, and then the one on the left is a negative 1.645. So a negative and a positive because they're symmetric. Okay. So it says if the area to the left is 0.0228, then the area to the right is, they are complements. So it's just 1 minus 0.0228. Which is 0.9772. So this area here is 0.9772. This area here. They are complements. If the area to the right is 0.012 over here, then what is the area to the left? Again, they're complements. And so that would be 0.9878. Let's move on to some scenarios where we have a little more context. So it's not just looking at the Z curve. So it says the final exam scores in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that a randomly selected student scored more than 65 on the exam. Let X equal a score on the final exam, and X is normally distributed with 63 as the mean, 5 as the standard deviation. Draw a graph. So we want more than 65, and the mean is at 63. Now, we don't have to draw all of the standard deviation markings, but I'm going to at least draw the mean and then the cutoff that I'm looking for. So 65 is bigger than the mean, and we want more than that. So that means I'm looking at this shaded area here. And symbolically, that probability looks like this. Probability of X greater than 65, because it is strictly greater than. We have no bound on the maximum, so we must use a positive infinity. Okay, this is what that looks like in Desmos. The normal disk, 63 and 5, and then 65 greater gives us 0.3446 rounded, or 34.46%. So the probability that a student scored greater than 65 on the exam where the mean is 63 and the standard deviation is 5 is 34.46%. Now, letter B says, find the probability that a randomly selected student scored less than 58 on the exam. So X is 58, and we're looking less than, so it's the area shaded to the left. So that means in Desmos, we're going to put in a negative infinity as our minimum. That's out here. And then our maximum is the 58. And that probability is 0.1587. And that is the area up here. Remember, area always is described on top of the curve, and your X or Z values are always described on the horizontal axis. So letter C says, find the 70th percentile. It says, for each problem or part of a problem, draw a new graph. Draw the x-axis, shade the area that corresponds to the 70th percentile. So we looked at percentiles earlier in chapter 2, and a percentile is where the percentage is the value where 70% of the data is at or below. So that would be a left tail. That would be this area here. So that's why I marked here 70%. So we're going to use, because we know the area and we want to find the X value, we want to find the score in the exam where students scored, 70% of the students scored less than, we're going to use the inverse with the mean at 63 and 5 and the area at 0.70. So that score would be 65.6. So 70% of the students scored less than 65.6%. Now, D says, find the score that marks the top 10%. So the top 10% means that we have 10% over here, but we have 90% below. And so we said earlier in Desmos, we could either type in the 90 for the left, or we could type in 1 minus 0.10. Either way, we're looking for this X value here. So the X value that goes with that would be a score of 69.41% on the exam. So you had to score almost 70 or better on the exam to be in the top 10%. Touch me back for beginning of example 9.